Before learning about voids, we must know what is meant by close packing and various close packed structures. Close packing in crystals refers to a space-efficient arrangement of the constituent particles in a crystal. That means the closest way to arrange the particles to minimize the vacant space. To minimize this empty space, the arrangement of these spheres must be very efficient. The sphere should be arranged as close together as possible to eliminate the empty spaces. So, before going to the three-dimensional or real close packed structure, we must know that from the basic thing, that is one-dimensional close packing. You can see here a one-dimensional close packing of the spheres. These spheres are arranged in a row. All the spheres are closely packed and are in contact with each other. So one sphere is in contact with the spheres to both sides. So there are two spheres or particles near any one of the sphere. So this makes the coordination number of one-dimensional structure is 2. What is actually meant by coordination number? The number of immediate neighbors to one particle is called coordination number. So in case of a one-dimensional close packing, it is 2. So for one particle, you can see there are 2 neighbors. When it comes to a two-dimensional wave, you can see these two arrangements. The first one is called a square close packing that forms, see, this forms a square. And we can see another one that is a hexagonal close packing. So in hexagonal close packing, in a square close packing, one particle is surrounded by 4 immediate neighbors. But in the case of a hexagonal close packing, you can see that one particle is surrounded by 6 immediate neighbors. So that forms a hexagonal arrangement like this. Comparing these two, you can see that in the case of a square close packing, the void, the space in between them is high compared to the hexagonal close packing occupies most spaces, or the void space is vacant space is less in case of hexagonal close packing. Now let us see the three-dimensional arrangement of close packed structures. So we already learned the arrangement in a plane. Now we can keep the next layer on the vacant side of the first layer, that is the B layer. So you can see the arrangement of B layer shown here. This is layer A and layer B shown. Now the selection of third layer, that actually determines whether the close packing belongs to hexagonal close packed HCP or face-centered cubic close packing structure. If you select a different third layer, that is a C layer, and keep on the interstitial or vacant sides of B layer, that will lead to a face-centered cubic or a cubic close packed structure. On the other hand, if you repeat the layer A on top of layer B, that will lead to the hexagonal close packed structure as shown here. So this is another view of hexagonal close pack and cubic close pack structure. In a hexagonal close pack structure, it is like A B formation. Like this it goes. This is the hexagonal close pack arrangement. Another thing you can see that if you consider this as one atom, I just marked it as number 1. How many immediate neighbors are there for it? There is 6 neighbors on its own B plane itself, and 3 at the bottom A plane and 3 on the top. So that is 3, 6 and 3. So what's the total number of neighbors? The total number of neighbors for HCP, hexagonal closed pack, is 12. That is the coordination number of the hexagonal closed pack structure is 12. On the other hand, you can see a cubic closed pack structure also. What is actually a cubic close? It is A, B, C, A, B, C formation. So here also you can see that one particular particle atom is surrounded by 6 on its own plane, 3 at the bottom A plane, and 3 on the C plane. So totally there are also 12 total number of immediate neighbors for this. You can see the arrangement in more detail here. This is our A, B arrangement. See how it forms a hexagonal close packing structure. Okay, 6 of one type and 3 of another type. This repeat. This is only one unit is shown here. And this hexagonal close packing has got a 6-fold axis of symmetry. So if you rotate this structure about an axis that passing through this, you see this is the axis shown here. Okay, if you rotate it, it has a 6-fold axis. Even if you 6-fold axis of symmetry, that is the term that we use for that. So even if you rotate one, this particle will come here, but that gives exactly same arrangement. One more time you rotate, the same arrangement, the similar. So 6 times you can, 6 type of rotation you can do about this axis that leads to the same arrangement. So a hexagonal close pack structure has got 6-fold axis of symmetry, that is represented as C6. On the other hand, a cubic close packing structure, we cannot select this axis there, this red color axis we cannot select there, because if you rotate about that axis, it will not give to a symmetry parameters. The neighbors are not same there, because it is ABC type of formation. So the better the axis for symmetry is this axis through the body diagonal. So you can rotate along this body diagonal. It has got a 3-fold axis of symmetry. So in 3 ways, you can rotate it to give a similar structure there. So it has got a 3-fold axis of symmetry. These are the FCC cubic close packing and hexagonal close packing structures again shown. And this table shows the coordination number. Coordination number means the number of immediate neighbors to one particle. And the packing efficiency. Packing efficiency means how the space is utilized. You can see that for a face-centered cubic, the packing efficiency is 0.74. That means 74% of the space is utilized, and the remaining 26% is vacant. That is the number packing efficiency represents. And you can see the face-centered cubic has got a coordination number of 12. Our next topic is voids. Any three-dimensional array of spheres give rise to void space or vacant space between them. These vacant spaces between the array of atoms or spheres are actually called the interstitial voids. There are mainly 2 types of interstitial voids. One is tetrahedral void and the other one is octahedral voids. A tetrahedral void is formed between 3 spheres on a close packed plane and a 4th sphere on an adjacent plane fitting in the cavity space between the 3 spheres. As you can see here, the 3 spheres, 1, 2, 3. So there is a space between them. So there is one on the top of that. So the space between these 4, that forms a tetrahedral void. It will be actually like centers of these three joint and then to the top. So it will be like these 3 in this way and then this forms. Okay, So this will be a tetrahedral void. There are actually two tetrahedral voids for every sphere in a three-dimensional array. For example, for a face-centered cubic unit cell, all the centers of tetrahedral void lie quarter way and three-quarter way along the four non-parallel body diagonals of the cube. So thus there are 8 tetrahedral voids in a unit cell. As the effective number of atoms in a unit cell is 4. In a face-centered cubic, the effective number of atoms is 4. How that 4? That is, you can see that 1 by 1 atom at the corner. One atom at the corner is actually divided into 8. So 1 by 8 times 8 plus, then at the centers of phase half are there. So 1 by 2 times, there are 6 phases. So what will be the total number? 1 plus 3, that is equal to 4. So that is why the effective number of atoms in a face-centered cube is 4. This is a face-centered cube. You can see this. Okay, so at the corners, even though 1 is there at each corner, for one unit cell only 1 by 8 of that will be in effect. Then at the center of phase, even though 1 is there at each phase, half only for one unit cell, the other half is for other unit cell. That is why 1 by 2 times 6. So totally 4 are there. So how the number of voids is 8 in an FCC. So you can see here it is there are 8 tetrahedral voids in a unit cell. So how? So you can see that there is one. This is the one such a structure. So you see one void there. Such how many voids are there? Such there will be 6 voids. 1, 2, 3, 4, 5. So there will be 6. There will be one here and one here. So totally there will be 6 plus 2, 8. So 8 tetrahedral voids in an FCC unit cell. An octahedral void is formed with 3 spheres on a close packed plane and 3 more spheres on the adjacent close packed plane. Like this. Comes like this 3. Then the next close packed will be like this. Okay. Note that these 3 spheres of adjacent planes are positioned such a way that the centers of 3 spheres are directly over the 3 triangular valleys surrounded by the central valley of the first plane. Nothing like this is one layer. Okay, and this is the center. This is the center. This is the center. But this is a valley point. This is a valley point. This is a valley point. So that at that valley point comes the center of the next sphere, like this. See, next this one, and next this one, like this. Okay. There is one octahedral void per sphere in the 3-dimensional array. For example, in an FCC unit cell, you can see an FCC unit cell here. It consists of 12 edges. So here one void. So actually 1/4 of that void belongs to that unit cell. Such 12 edges are there. So 1/4 times 12 voids are there. And there is one at the center of the body. So 1 plus 12 times 1 by 4. So totally 4 octahedral voids are there in one unit cell of FCC. So this is actually equal to the effective number of atoms in the unit cell. The effective number of atoms in an FCC is also 4. This is a brief description of the 2 types of voids we learned, tetrahedral voids and octahedral voids, and the coordination number and the number of voids in. If you're considering a cubic close packed structure, the tetrahedral voids are equal to 2 times number of atoms in the unit cell. We know that in a cubic closed pack, a face-centered cubic, there are 4 atoms in a unit cell. So there are 8 voids. At the same time, when you consider the octahedral void, it is equivalent to the number of voids are 1 times the number of atoms in unit cell. So in the case of FCC, if you consider, it is 1 times 4, that is 4. Now, our next aim is to find the size of a void. We already learned what is meant by void and what are the different types of void. Now, what is the size of a void? The radius of largest sphere that can fit inside the void, inside the vacant space, without displacing the spheres at the corners, defining the void. So, which all sphere that define the void without altering that structure, the size of the largest sphere that we can keep inside this space. That is actually called size of a void. So we are going to find the size of a tetrahedral void first. You can see an atom of size 2r. So formation of a tetrahedral void is more detail explained here. You can see the first layer there, the layer here. So each radius r and r, so the distance between them is equal to 2r. We generally call this as A. Here A is 2 times the R. Okay. Now you can see how the triangle formed EFG. Okay. Now the next layer is kept on the valley of these 3. This is the valley of the 3. So we are going to keep the next layer on the top of that. The B layer. The center of this atom also along with the other 3 centers forms the tetrahedral void that is shown here, and H is the vertex. So you can see the tetrahedral void with EFG, the green color base. Now we have to find the size of the largest sphere that can occur or that we can keep in this void space. So first of all, for finding the size, we need to position the center. So first I'm considering the base EFG, the triangular base, and draw a perpendicular from G to the side EF that we can see as the height of the base triangle only. And Q, the point Q is the centroid that divides the height in the ratio 2:1. So applying Pythagoras theorem, we can write GP equal to square root of hypotenuse square minus base square. So this is 2r, so 2r square, so 4r square minus r square, root 3r. And Q is the centroid, therefore GQ is equal to, Q actually divides the line in the ratio 2/3 and 1/3. So 2/3 times GP, so 2/3 times root 3r, that is 2/3 times r. So we got the centroid of the base triangle. Now we are extending that to the pyramidal shape, the tetrahedral shape. So drawing a perpendicular from the vertex H to the base, that is at the point Q, where Q is the centroid of the base. And you can see the point T here. T is the centroid of the line HQ, or that point T divides this line in the ratio 3:1. So we have to calculate HT. First we have to calculate HQ, again by using the Pythagoras theorem method. So HQ is equal to square root of HG square minus QG square. Substitute 2r square is 4r square, and this is 2/root 3 times r, so that is why square is this, and simplified to get HQ. then ht is equal to 3 over 4, because t divides that line in the ratio into 3 by 4 and 1 by 4. So 3 by 4 times hq, that is root of 3 over 2 times r. Now you can see that the tetrahedral void with T as the centroid. So we know that at the vertex H, E, F, and G, spheres are there. The spheres that, or the atoms that makes the crystal unit cell. So the green color one is the sphere or the atom, and the blue color one is the maximum, the largest sphere that we can keep at the void. Now, the length between H and T, the length between H and T is actually filled with one R, and another is RT. RT is actually the radius of the largest sphere, or it is the size of the void. So, we already calculated HT. So, here HT is equal to R plus small rt. And HT is substituted from the previous calculation, root 3 over root 2 times R, and simplified to get RT. The size of the tetrahedral void is 0.225 times R, capital R, where capital R is the size of the atom that constitute this particular unit cell. Next, let us move to determination of size of an octahedral void. We already defined what is an octahedral void. Now we are at the stage to define the size of an octahedral void. As the definition of a size we already learned, it is the size of the maximum size, the radius of the maximum sized sphere that can occupy the void formed by spheres at the corners. So we know that octahedral voids are formed by the AB, AB, AB layer formation. So here you can see one such layer, A layer, and their centers joined. And the next you can see the vacant sides are occupied, or over that first layer, the B layer is kept, and their centers are joined. This is the basic formation of an octahedral void. So for making the calculation of the size simpler, we can draw an octahedral void in this way also, using four spheres. So you can see the four spheres occupied at the four corners of a square, as shown here. So we know the radius of each sphere is r. Therefore, the size of one side of the square will be 2r. The next one also will be 2r. So what will be the maximum sized sphere that can occupy this void site here? It will be like this, right? Yeah. And the size, the radius, let that radius be r0, the radius of the maximum sized sphere that can occupy an octahedral void. So we have to calculate the size of the maximum sized sphere that can fit in this void, this octahedral void. So you can see that the diagonal, the full diagonal of this square, that consists of one r here, another r, and this is equal to 2r0. So from the using the Pythagoras method, we can find the length of the diagonal, that is 2r square plus 2r square under root. That gives to square root of 8r square. That is equal to 2 root 2 times r. Now we already know that the diagonal is equal to r plus 2r0. R plus 2r0. That is equal to the length 2 root 2 times r. So on simplifying this, we'll get r 2r0 equal to 2 root 2r minus 2r, and that is equal to, we can divide with the 2, you'll give root 2 minus 1 times r, or that is equal to 0.414 r. So this is the size of an octahedral void. R0 equal to 0.414 times capital R, where capital R is the size of the particle that forms this void. It depends on which material is there in this crystal. Now we can try a problem to find C by A ratio of a ideally packed HCP crystal. And HCP is also known as a bipyramidal shape. You can see there are two pyramids, one up and one down. So how to find the uh, C by A ratio? So C is actually the length between the two. This is C, and A is the unit cell dimensions. So that is, in this diagram it is P to P, that is C, but we can see it as 2 times PT, that also will give the answer, right? Divided by RS or QS or QR, so divided by RS. Now, how to find PT? We already did this calculations based on the centroid, and also PT, the length of PT is already calculated. So we need to get that value of PT. PT is actually the height of one pyramid. So that is equal to root 2 over root 3 times A. We already did this calculation. You can refer the previous slides. And RS is already A. I think we used R, the term R there to calculate. So here they use A. Okay. I think we got root 2 over root 3 times R in the previous slide. So in this, they used A as usual instead of R. The lattice parameter A can be used for this. Okay. So therefore, the C by A ratio will be 2 times root 2 over root 3 times A divided by A. A gets cancelled. So that will be 2 root 2 divided by 2 root 2 divided by root 3. So that will be equal to 1.633 to find C by A ratio. Okay. Thank you.